Let's go to question number 67, and I'll take a bit different system for the work energy theorem. I'll choose a system, right? And the previous question, quite similar. I considered the circuits to be part of the system, not the external. But the standard way too, it was not wrong, but the standard way is you take the circuit also to be an external, and the electric fields are taken internal, and that's how you use the work energy. You'll get the same answer anyways. Okay, so the question number 67 is it's like if you have done the previous question and the example number 22, it's quite easy. You use the same formulas, same derivations. It's just by the way I have solved. I do not know if there's a different way some other has solved and they're not using the same formulas. I am using the same formulas the way I have solved. So I'll just explain my way. There is a capacitor which I'll draw with a red because why not? So this answer has a bit of ambiguity. Why I'll tell at last. Because it relies on one thing that the K2 this K2 dielectric doesn't come over here. Right. And I'll tell you my way. I have not seen the actual solutions. Maybe I'm wrong. I'll see the actual solutions written by actual people after that. But anyways, solutions are written by actual people. I mean, the YouTube channels यहाँ पे solutions होते हैं. उसके बाद देखो. I'll just tell you my way. So, see, this is the configuration. You have a dielectric and it is equally divided between two capacitors. I'm not saying कि ये half space occupy करता है, but if there's a capacitor, मानो ये 50 सेंटीमीटर का, of course ये तो बहुत ही बड़ा होता है dielectric से, that's how you use the formula. Otherwise, corners around electric field would be a bit different, but uh, it's dielectric is small as compared to the plates, but it is equally divided. K1 is here and K2 is there, right? So you know the force by a capacitor on a dielectric is attractive if it's not completely inserted. It's attractive. And there are two these attractive forces on this dielectric, one from this side, one from this side. We are saying for equilibrium, find the ratios of the electromotive force of the battery. Let's say it's V1 and it's V2, and we have to find the ratio V1 by V2 for its equilibrium. Now you can solve, though it is one capacitor. See, this is one dielectric only, not capacitor. This is one dielectric only, but I'll still divide it into two parts. That's why I've used the different colors. It's the same dielectric, but I'll use different colors. I'll divide it into two parts. You can, there's nothing wrong. One is this red one, and this is blue one. It's kind of resembles a magnet now, but anyways, see what happens is this K2 part, because there's some kind of attractive force here, right? This K2 part pulls. What's called? It's called tensile stress, if I'm not wrong. Tensile stress. Yeah, when I'm pulling forces up, right? So there's some kind of course, the Young's modulus. We do not have elasticity here. So this is it's pulling the K1. K2 is pulling this K1 by some force. And similarly, by Newton's third law, this K1 is also pulling K2 by the same force. I'm assuming that force is K. Oh, sorry, that's not K because in confusion, let's say it is F. So this K1 is getting pulled here by F, and this K2 is getting pulled here by the same F. Now, let's say the whole system in equilibrium, we can have velocity, constant velocity. It's moving left It's moving left and you're moving left. Let's say you cover a distance dx. If this is say x, you will not integrate, will not differentiate actually. use नहीं होगा because of the way I derived the previous question number 66. You do not need calculus for this question. Okay, anyways, so now I'll not consider the battery to be an internal force. It will cause a bit of confusion. That's not wrong. I'll say the electric field is internal, battery and this FR external. So because it's moving in the direction, and this F comes here. This K1 comes a bit here. By the way, I derived in question number 67. If you don't know, if you have are doing this, you may have done question number 67, but if you have done by yourself, then there should be no confusion. But watch my previous video if you want to know how I'm deriving for DC. But anyways, so this force F in the direction, now it's increasing. See, plus I'll say I'm saying the external work. I'm saying the external forces is the force F and the work on my battery. They are external works. You can say the external work done is the change. So what do you have? What kind of formula? The change in potential energy is the work by external. So I'm saying the work on my battery is external, not internal. Like I solved for the question number 66. The work on my battery is of course what? DC V1, the charge and it's going through V1, so V1 square is equal to change in kinetic energy, which is half DC V1 square. F dx, sorry, this minus, it's not plus because see, there is a tensor adjust. It's this K2 is pulling it, the external force is pulling it. I saw this. The external force is pulling it to the right, but it's moving to the left by my assumption. It should be minus F dx, sorry. Is equal to minus half dCV square, V2 square. Oh, sorry, V1 square. I think I have written V1 square. So F dx equal to half dc V1 square. Now dc, it's what's B is the width, it's not given. So B dx epsilon naught by D is the capacitor, is the extra capacitor being created. If you want to know how, and B dx epsilon naught by D is the capacitor being reduced. If you want to know how, then watch my previous video. I've taken alpha, beta, gamma and explained you thoroughly why this works. It can be intuitive if you have solved a lot of questions. See this capacitor is being created and this capacitor, the air which was it's getting subtracted and this is the change in capacitor. We just want to know the change. So it's DC or DC is equal to B dx epsilon naught by D K minus 1. So you put it here and you do not need to differentiate or something like that. B dx epsilon naught by t k minus 1 v1 square, and of course this is k1, right? K1 is moving here, and you cut dx by this dx. You can assume delta x if you do not want, if you want to be purely mathematical. B epsilon naught, so let's kind of stack it. So F is equal to B epsilon naught v1 square k minus 1 d by 2d. Similarly, for this blue color plate, we have there this K1 is applying a force F here, and it is moving here because I assume the whole dielectric is moving to the left, so it is moving here. Now the work done is positive. The work done by external force is F dx plus, and it's of course if it's moving by dx, it should also move F dx plus the work done by this battery. Of course, this is the see this electric field is the internal system. इस पे ये काम कर रहा है. This battery is doing work and this F is doing work. This F is doing work. There are no other forces. So F dx plus half dc V2 square, sorry, not half, क्या कर रहा हूँ मैं? It's just DC V2 square over my battery rate is equal to the change in potential energy, which is half DC V2 square. Now you need not know if it's positive or negative. Uh, the same way, there's a negative sign. You calculate DC. This is not the same DC. If that was DC1, it is DC2. I can write DC2 as a variable. DC2 is, of course, air is getting added and the dielectric is getting subtracted. So the same formula you have B dx epsilon naught by D is getting added, and what we are is getting subtracted. K2 B dx epsilon naught by D is getting subtracted. So B dx epsilon naught by D 1 minus K2. And of course, K2 is always greater than 1, so it is minus. So we'll get the answer as plus. Minus half D C2, this DC2. It's how much is B dx epsilon naught by D 1 minus K2. तो आप माइनस अंदर ले जाओ, अच्छा V2 स्क्वायर का रहेगा, and you take the minus inside, it becomes K2 minus 1. So you cut dx, let's tag them. And see, these are F is same, so you equate both of these equations. B epsilon naught by 2D, B epsilon naught by 2D will get cut. So what will remain is, I should rather, which color, let's use yellow. So B epsilon naught by 2D वो तो कट जाएंगे, and we have K2 minus 1 V2 square equal to K1 minus 1 V1 square. तो V1 by V2 पूछे, इसको V1 माना हमने, तो V1 by V2 equal to root K2 minus 1 on K1 minus 1, K2 minus 1 on K1 minus 1, and this is the correct answer. Right. Just one ambiguity, some ambiguity that we have assumed this dx should be so small such that this K2 part doesn't get to that capacity. But if we are assuming it's moving by some constant velocity, then this K2 will eventually come here. And this K2, when it will come here, of course, we're not sure if it completely leaves this part, but it will eventually come here, and so there will be K1, K2. Maybe we can use the same formulas and derive something, and maybe we'll get the same answer. I don't know, I haven't solved that much. I can solve it now. Let's say this K2 jumps and comes here. What about that? If this K2 jumps here, uh, if this K2 jumps here, this was not part of the initial plan. I may be impromptu. It's basically improvisation. So let's see if something works out. If it works out, then it's okay. If something doesn't, then I'll just cut this part. So let's try. Let's try कि कुछ निकल जाए. Maybe we'll get the same answer. Maybe, maybe not. What was this? This was K1 and this was K2, right? Well, it has moved inside. मैंने ज़्यादा inside नहीं बनाया, but it has come. Now what happens? The DC for the first one, it's not just it's not just what do we say? B dx epsilon naught by d, जैसे k1 तो ऐड हो ही रहे हैं, k1 तो ऐड हो ही रहे हैं, but some kind of k2 is also being subtract, some k1 is also being subtracted, so k1 में तो कोई प्रॉब्लम नहीं, see ये वाला k1 तो will be intact, no more k1 will come inside, अब जो come inside होगा वो k2 होगा, तो यहाँ पर जो k1 क्रिएट होगा और यहाँ पर जो k1 लॉस होगा वो देर will counteract, right? So there will be no change in k1, I guess. There will just be a change in k2. So of course, f here and f here, and of course we have b dx epsilon naught by d. So k2, I think I'll get the opposite answer. K1 minus 1 upon k2 minus 1. Let's see. B dx epsilon naught, that's just my intuition. K2 minus 1 dc1, and if you put that into the formula once again, this is the external force. Should it be considered internal force that has, no, it should be. So f dx, and of course it's coming inside when the tensile force is putting it here, minus f dx. Hmm. F x plus, rolled on my battery is dc 1 square is equal to half dc 1 square. Hmm. So f dx is once again half dc 1 square, and dc is by putting that, by putting this thing off, a2 minus 1. Now I think v1 square, and v1 square के साथ we have k2. Number v1 so there साथ we had v1. Now we have k2. Amazing. Amazing. I think maybe I could have done something wrong. This is the external force, and by this external force I've got dx. External force. What would I by external force? I don't know. So, and you may use that same formula. यहाँ से वो subtract ही हो रहा है. अच्छा, then we'll get 1, I guess. Yeah, then we'll get 1. So, but equilibrium, maybe I just assuming constant velocity. It it may not be. Yeah, it may be just have zero velocity, and so we do not have to use this. Otherwise, अब यहाँ पर तो यार देखो यहाँ पर we'll use, of course, यहाँ पर subtract ही हो रहा है. तो यहाँ पर भी वही half b epsilon naught by d k2 minus 1 v2 square, and we'll add, and this is basically the same thing. Uh, so except v1 v2, so v1 square by v2 square is 1 in that case. When if it completely moves to here by my derivation, it may be wrong, I don't know, but I think we'll just assume it's stationary, not just an equilibrium. Yeah, it's stationary, right? Maybe we'll solve for that only. We are just assume constant velocity for calculation sake, but we can assume that constant velocity. We can assume initially it was stationary, so finally it will also be stationary, and this formula works all right. We assume constant velocity just for solution sake, not actually we put it in the constant velocity. Okay, bye.